Yeah, so our second talk of the today's morning session is by Professor Samuel Lafon from Université Grenoble Alpes, France. And he will be speaking on the principles of quadratic Chabauty and non-split Cartan modular curves. It's over to you.
All right. Thank you very much. Happy to be here for the second week. Most of you were already here last week. So some of the things I'll talk about, I'll just skip over them because we mentioned them in more or less detail last week. But to give first a bit of the description, I want to explain not exactly quadratic Chabauty itself, but in the case of non-split Cartan model curves, which is of great interest for many people, how could it apply? How does it apply? And what is the hope for what's next? All right. So what I'll explain comes from a joint work with Nathan Dogra. And first, because I'm one of the first speakers in the week, I'll do some motivation and history to recall some notation which might be useful afterwards. So this is sort of a very short introduction to what happened for modular curves in the last 50 years. So I have to be efficient. Okay, so the first of all motivations is the study of Galois representations coming from elliptic curves in this way. So you start with E over Q, an elliptic curve, and P prime. How can you build a Galois representation from this? Well, it's not too difficult. You consider the P torsion of E, which is actually as a group isomorphic to Fp square. Okay, and the Galois group of Q acts on this linearly, and I call it GQ here. So this defines, after choice of basis, this defines rho EP from GQ to GR2 of FP. This is our Galois representation. And in some sense, as opposed to a previous talk, the questions we'll ask is sort of basic afterwards. It's what is the image? So the short version has been solved a while ago now by IISER, that if E is not CM, there exists a constant, let's say bound B of E, such that if P is larger than this bound, rho EP is surjective. Okay, but the nature of its proof clearly depends on E. You have some information, for example, related to the height of E in some sense, etc. So you have a bound that depends on E, and it's not clear it's really necessary. So this raised uniformity problem, one called Serre's uniformity problem. Here. So, which is basically, can we have a uniform bound? In other words, when you make this not dependent on E, or any curve of a Q not CM, is there a prime P, a bound after which rho P is surjective? And to give you a maybe more concrete idea, we think, I think people who work on it think P larger than 37 seems a good candidate. Right? Okay. Actually, we can split this problem in very natural way because, well, we're looking at the image of rho EP, and rho EP is inside GL2. And so we just have to figure out what are the main proper subgroups, maximal proper subgroups for GL2. Okay. And for determinant reasons, which because we know basically what happens with determinants, this splits the problem into 4 parts. 4 types of maximal subgroups with some additional property for a determinant that we know with this here. Subgroups of GL2 FP, of course proper. The first type is Borel subgroup, which is basically up to conjugation upper triangle matrices. And what will happen here is that if the image of rho EP is inside one of those subgroups, it means there is something preserved by the Galois action. And if I translate it properly, it will mean it defines a point on a modular curve. And here, Borel defines this kind of subgroup, actually defines a point on x naught of P, which we already heard about a lot. Second type is normalizer of split Cartan subgroup. Well, this is basically up to conjugation again, so a good choice of basis. Diagonal or anti-diagonal matrices. Looking at what this means in terms of a modular curve, we get this curve, which we encountered also last week, which is x split plus of P. When we don't put the plus, it's just because we consider only this group. Only the split Cartan is this, normalizer is the whole group here. A third type, normalizer of non-split Cartan, which is slightly harder to describe, but what I find is the most natural way is that FP square, well, as a space, you can also think of one other space that looks like this. It is FP square, so the field with P square elements. Because of this, you can make FP square act on itself by multiplication. And if you choose a basis, it will define an image of a subgroup inside this. This is how you can define a non-split Cartan subgroup. A normalizer is either you think about taking the Frobenius, which is sort of an anti-automorphism, or you can also think about normalizing inside this, and you also have an extension, well, a subgroup, which is of index 2 in a normalizer. So basically here, TNS of P, which is sort of a copy of F P square star in GL2 of FP, and CNS plus of P, CNS of P of index 2 in it. I'll not say much more about the description because I don't need it, but basically that's it. And the final group, type of group, which is exceptional here. In one sentence, when you projectivize, when you like PG inside PGL2 of FP, the image could be A4, S4, or A5 sometimes. And this is called exceptional. But this is easy and actually already treated in this paper. So we will not care about it. So now maybe I'll pick one page because I will do some sort of table to sum up the results here. Yeah, and here this is obviously called modular curve. Here is a x and s plus of P. All right. Yeah. First, maybe before I give the table, I'll just start with the first curve. So this one, which you know already much. So recall last week, the Chabauty-Coleman method. So if R the rank of a Jacobian J, so C over Q curve here. If the rank of the Jacobian is less than G, the genus of C, you can, in principle, let's say, I'm being a bit vague here, determine C of Q. We can get a bound on the number, and in practice, if we have equations, we can compute the points with a bit of luck. Okay, I just do a remark here. Actually, you don't really need the whole rank of the Jacobian to be less than the genus. It's enough to have a quotient abelian variety A here. Such that the rank A of Q is less than the dimension A, which is the same thing as here, if you remember that G is also the dimension of the Jacobian J. Yes. So if you have just this for a quotient, which can happen sometimes, well, you can still apply the method, and you can still hope to determine the set of rational points. Even better, it's even easier to apply if the rank is as small as it can be, meaning 0. Okay, and if the rank is 0, we call this a rank 0 quotient, and we hope we can apply this. And that was, well, I guess, one of the many ideas in Mazur's results in the 70s. So this is how I start my table. So I have 3 columns, 4 with the actual results. So I will be looking at these 3 families of modular curves. So x naught of P, x at P plus of P, and x and s plus of P here. And I will try to give very short indications about what the method we can use to figure out the rational points. What does the method need? And what is the range of known results? Okay, so if you think about that here, the first idea would be, okay, can we apply some kind of Chabauty common method to x naught of P? And if you understood what I just said here, can we find a rank less than dimension quotient? And we can even ask, can we find a rank 0 quotient? Answer is yes. So this was successfully applied by Mazur in 1977. And what he needed was a rank 0 quotient. And he proved it existed. Like mentioned it a bit, it's the Eisenstein ideal, so it's also related to the Eisenstein quotient. Here, so it exists. So Mazur, which is basically contains Chabauty in this case, plus expansion, plus many other tools. Okay, but I will insist here on the what happens with the quotients of a Boolean variety. So this part of the proof, there is no rank 0 quotient. So the results he obtained are true at least for every prime larger than 13, and he's proven that x naught of P of Q is only made up of basically the rational points we expect, starting at 13. And there are some rational points above 13, but they are all CM points. So basically, we know the answer to this problem, to this part of the problem for Borel. So this solves this part. Okay, so here we're good for P larger than 13. And of course, the small primes we already knew. We can compute them, etc. We can compute all the points here. All right, now the second one. I'll just mention some things, and afterwards I'll discuss about this existence and how we know this. For the second one, also mentioned by Luc before, we also know what happens for XSP plus P by the arguments of Bilu-Parent and concluded by Bilu-Parent and Reboledo. Here, much tighter. So 2013. And if I had to drop another name in there, I would say maybe Momose, which has done a lot of work on this decades ago. And so the question might be, okay, how does it resemble the method? Actually, it's an adapted version of this method to this kind of curves. And in particular, well, is there rank zero quotient here? The answer is yes, and it's actually the same. And I'll explain why. This one has been reused. Yeah, at least we can reuse this one. We can also use another one, which I'll sort of mention afterwards. But this one can be used again. All right. And now, what's the state of the last family here? Well, again, I'll explain what happens in the second line here. But here, what we can definitely say, at least in its current state, is that Mazur's method fails for this curve. And why does it fail? Because we expect no rank less than dimension quotient. Okay, let's say in a little writing, let's say under BSD, okay? But believe, well, I guess you will accept that if we have managed to find something accidentally like this, it will mean that we break BSD, and I think it will be a more interesting result than everything I could say in the next hour. So let's just assume that BSD is true and say drawing less than dimension quotient. All right, so for now, it seems we've been a bit stuck. But first, I'll explain how do we know this line. So, about the ranks. Again, it's been sort of mentioned right before. And here for me, sorry, my notation is a bit different. For me, n is equal to p or p square, not q. So you have to adapt. So this is a level. And I take f an eigenform. So a new here. In particular, here, because it's a new eigenform, I have that's when I apply the Frico involution, it's plus or minus itself. All right, this defines me very naturally plus and minus spaces here. So I will denote plus for the spaces where I get plus f and minus for the space where I get minus f, of course. This is useful later. And then if I look at the completed L function to simplify the expression of f, I get this. The completed L function at 2 minus s is minus epsilon times the completed function at s. Here. Basically, that's the argument you've seen. And for us, we're interested in the case s is equal to 1. And if followed, for s is equal to 1, what happens is that if epsilon is plus 1, we get necessarily this is equal to 0 by sign argument. For epsilon is minus 1, we have a hope of this being non-zero at 1. Okay. Let's say yes. This implies epsilon is equal to 1. This must be 0. All right. And furthermore, I'll also say this right now, but it's out of the way. This is one implication, and it's combined with great profit. And this was very present in the, I think, third lecture of Jan's last week. Kolbegin and Logachev based on Gros-Zagier formula, but with much more work afterwards still. In the 90s, here, said that if AF, so a abelian variety, is a abelian variety of quotients of genus of n attached to F. Okay, so I can always attach to an eigenform an abelian variety, which is a quotient of a genus of n here. Well, if I look at the rank of L of S at S is equal to 1, I know what happens in two cases. The first obvious case is when it's 0. In other words, if the rank is 0, it means that L of F1 is 0, is non-zero, sorry. Here. In this case, I know that the rank of AF of Q is 0 as well. Okay, so I do get the rank 0 quotients sort of magically. And if the rank of L of Fs is equal to 1 here, well, we know as well what happens. And here, to be a bit careful, it's not the rank is equal to 1, it's the rank is equal to dimension here. And this is because, in fact, F can have non-integral coefficients and they are conjugates. And in some sense, all the conjugates participate to the L function of A here. Maybe I should say it right now, and call that dimension of AF is equal to the degree of the field here, where Kf is generated by the coefficients of F in the in the Q expansion. Okay, so I have a field generated by this. So dimension of AF is this, and even more actually, and it will be useful for later. What could justify that it's dimension and not 1, intuitively at least? It's that the endomorphism of AF tends to Q, it's exactly the same as KF in this case. Okay, so if I think about rational points here, they are a tensor Q, it's a KF vector space. So it must have a dimension that's multiple of this degree. Okay, so this degree is also the area. This degree is the dimension. So it's normal that I don't get 1, but I do get dimension. All right, now I'm ready to explain what happens in here. So now I should make clear, Eisenstein quotient was built by a very tricky and very, very special argument for extents of P. So IISER did not have this on the hand. It was before. So he managed to find still a way to construct a quotient. But now we have a sort of better procedure because we look at every F such that L of F1 is non-zero, and we put the AFs together. And this gives us something which is by construction of rank 0, if it's non-trivial. And it's called the winding quotient. All right. So rank 0 will do anyway here. So why does it exist? Well, IISER proved it exists. And I haven't explained here yet this and this side. So I'll do it right now. And it's because actually the 3 Jacobians of the families of modular curves I mentioned here are related. So I sort of have, can write everything with those 3. So furthermore, as a fact here, I know that there exists an isogeny, actually isogenies, because I write several of them. So the Jacobian of SP plus of P, okay, so the one in the middle, is actually isogenous to the Jacobian of NSP plus of P times J naught of P. Okay, so in some sense, the one in the middle, in terms of Jacobian, is the product of the ones here. In particular, it contains J naught of P as a quotient, which means if I have found a rank 0 quotient here, I have found a rank 0 quotient here. Okay, so this explains why I say reused in the middle column. Now I don't still know enough of this, but actually this is isogynous to J naught of P square plus nu. And if I want to be complete, here is it all makes sense. This is net of P plus. And these will be found by 10. These are isogenies. And later expanded or maybe more formal by De Smit and Elixoven. All right, so to fix the ideas now, I know there is a rank 0 quotient here. I can reuse it in here because the Jacobian is strictly bigger, but the other part of the Jacobian is this one. And it's actually the same as J naught of P square plus nu. Now what happens? Let's look at a modular form here in gamma naught of P square plus nu. All right. As I said here, what happens is that L, the epsilon has to be plus. So here I get a sign -1. So it means I'm compelled to have L of F1 is equal to 0. Okay, equal to 0 forces me to not have a rank 0 quotient as expected by this. And if we believe BSD, it's actually, it will be a multiple of the analytic rank of L at 1. Right, so it's not here, this is where the problem lies. So here, no expected rank less than dimension quotient because of the signs of the L functions. Okay. So this was where we were at, I'd say, until 2015 or so. We're stuck here because no small rank quotient. So it was not clear what could we do. And that's when quadratic Chabauty comes into play. That's what I'm going to talk about now, briefly. Yeah, the range of the right. Yeah, it's good here. So what does it tell us? Quadratic Chabauty. Here. So this method, I should say at first, has been developed by many people. I will name some of them. I hope do not forget anyone here. That's Balakrishnan, Lesser, Bagra, Mueller, Whitman, and Vonk. So since 2015, I think. I'll maybe first state the main accomplishments or our problems, and then explain how it was possible. So in 2019, 5 of these authors managed to determine X and S plus of 13, which has resisted a very long time to all other approaches. All right. And they did it again, I think this year, or the next one, which is for P is equal to 17. Okay, so this adds at least in the range what we have here. Know what happens, but how? Let's put it in red to say it's already the new Okay. What quadratic Chabauty does that classical Chabauty does not, as a reminder, even if we're not here last week, is that the hypothesis is slightly weaker, and it's enough for us. So we'll just take it as a black box here. So define rho J as the rank of the Néron-Severi group of J, which is this quotient. It can be proven it's a finite type Z module. So we can define its rank, and we call this a Picard number here. But you can also see it in another way. It's the same thing as the rank of some subring of endomorphisms, symmetric endomorphisms in some sense. I will not explain of what it means, but you can see this as endomorphism. Okay, so it's also a rank of a sub-ring of endomorphisms of J. All right, and what it says that if R, so let's say R is the rank of J of Q here, if R is less than G, this was alone the classical Chabauty condition, but I add rho J minus 1, then we can apply quadratic Chabauty. This will be the QC hypothesis. And determine here, in principle, P of Q. Here I'm voluntarily vague, and this is also why I said principle in the title, because I'm not pretending we determine anything in practice. Okay, it's just the method works, the method proves finiteness, and there is even a result at the end, which I hope to get to, but it doesn't replace the fact that you have to compute with equations and do the actual, quite difficult work to figuring out what it tells us. Okay, which is in principle. All right. Maybe as a small remark here, of course, for 13 and 17, we can compute the ranks, and I guess here it works for the Jacobian itself, no problem. But imagine we want a result in families. So for P large, this, we want to understand what happens with the J of P. It's not clear what we can do, right? And actually, I think even now, under BSD, we know a bit of things, but we might not know enough, at least for small p's, right? So it's not really a good condition for us. For a Jacobian of a modular curve with P going to infinity, it's really a hard problem to tackle. So the hope is, can we do this, but for a quotient, as before? Because it's actually the same for generators of P. We don't really know that well the full Jacobian, but we were happy enough to say there is a rank 0 quotient and work with this. Okay, because, well, at least this was more manageable. There we hope to do the same. So of course there is no rank 0 quotient, but the best thing there is would be, instead of this, a smaller condition would be rank is equal to G and rho is larger than 1. Okay, it's enough to get this, and we hope to get a quotient doing this. And I'll explain right now what's going on when I try to do this. Yeah, and to explain this, so this was the version developed originally. As I explained last week, there is an alternative version, which is a reinterpretation of many things here by Besser, Müller, and Universal, and developed this year, which I will not say much, especially because Narasimha is going to talk, I think, Thursday about this. So she'll do a much better job on this than me. But basically, it uses p-adic heights and works as this works as well when rank is equal to G and and there exists a L inside Picard group of J and not inside the Picard group of 0 of J with A star L is trivial, where I will be an Abel Jacobi map. Okay, so I inject C to J with the help of some base points here, which I choose, and I pull back this, and I want to some L to exist so that this is trivial. When this is done, I can use the p-adic adelic heights to get a height on the points of the curve, p-adic, and compare it with other data and get equations and figure out finiteness here. I'm doing a very rough summary, but we've seen more of this last week. Okay, we want this to work for a quotient. And I explain also how to get this from the information on neuron several groups. Okay. And again, it helps to think about the classical case. In the classical case, I take a quotient of rank 0, it's good. Even of rank less than dimension. The method extends, just you have found sort of shortcut to exploit this. So assume I have a morphism applied to A, and row A is larger than 1, and rank A of Q is the dimension. Okay, so you assume the same hypothesis, but for A instead of J. The goal is to figure out, can we apply the method? Well, we do want something like this. And we know that if we find function L, but in peak of A, with the pullback trivial, we will be able to apply the same techniques. So what is the sort of problem with this? Let's start. So let's start with LA here inside this space. So first, I have the peak of A divided by peak 0 of A is a neuron cell group here. I can pull back by the phi here, which goes to NS of J. Itself, I pull back by I star. It goes to NS of C, which is now the same thing as the degree. Okay. As an obvious implication, if something is trivial here, you want it to be at least of degree 0, right? Be sure it has a chance to be trivial. So you start with this, and you want something that can be sent from there to there, and being non-zero in this group. Well, this is okay because I assumed row A is larger than 1, which means this is a Z modulo of rank at least 2, and this is of rank 1, of course. So there is some A here, right, and non-zero. All right, which means now, it means if I follow all this, so I take its pullback here, and then its pullback here. It's inside peak 0 of C. Okay, because it's of degree 0 here. It's the same as peak 0. And I want this to be actually trivial. So of course, I don't expect it to be trivial miraculously from the first here. But what I want to do is to modify this LA so that this becomes actually trivial there. Okay, to modify while staying in the same class. So it means, can we take M A inside peak 0 of A? So in the kernel, it's in peak 0 here. That's I star LA tensor M would be now trivial. Okay, that's what we want to do. We want to make sure that we get a trivial manual shear. Well, it turns out there is a sort of weird obstruction to that. Something is going on. And I can explain quite easily, because if you modify this, what happens to this kind of maps? So now it goes from peak 0 of A to peak 0 J and peak 0 of C. If I start with MA, I get there. Actually, we know what this is, because this is the rational points of the dual of A. This rational points of the dual of J, and this rational points of J. And I get maps, I mean, algebraic maps here. All right. Well, it's slightly different of what I expected. First, J dual and J are isomorphic, and this is one of the isomorphisms. So this is actually an isomorphism. And now A dual, I need to compare it to A. But A dual, it's actually isogenous to A, so I get, let's say, an isogeny sending, and this means it's part of a map going from A to J. Okay, but now there is a problem, and I'll explain right here. That's what I do. Yes, let's finish it here. Let's write J as A times B here, and assume that A and B do not see each other, which means there are no homomorphisms from A to B. There, maybe in the Q bar over Q bar and here. What happens? There, if I start to go with an MA here and send it inside this by pullbacks, it means I'm looking at the restriction of such a morphism, A dual to J. But because A and B do not share any factors, it will actually send me then iota star pi star of MA belongs to A of Q. Okay, so the image, the image of A of Q inside this, so say pi B here, pi. So I can, up to torsion, I can identify A of Q as inside J of Q, and because of this, it's functorial in this sense. It sends A to J a bit as before, so there is no B of Q part when I do that, which is natural. I mean, looking at duals of abelian varieties. But now there is a problem. This works for the peak 0. It has no reason to work above for these ones. Even if I start with an Li like this, it's not clear why this should land so big. Again, now I should say this is J of Q. It's not clear why this should land inside A of Q. And we can even find some counterexamples. Basically, if you try to understand what's going on, there is something which looks very much non-factorial there. So there is a bit weirdly, there is no clear reason why it should be in A of Q. All right, so if you start in A of Q, you cannot use MA to modify and to get to 0, right? So that's actually the right hypothesis here. So I'll write it. Here. The right hypothesis is to ask for LA, who's not only inside this kernel, but that's this lands inside A of Q. We need to ask it. Or LA inside peak 0 minus peak 0, such that the pullbacks here belongs in A of Q inside J of Q. Once you have done all the identifications, it might be up to torsion, etc. But the idea is J of Q split in 2 parts, and you want this inside to be in parts related to A. If it is, then you can use a MA, because this is isogeny, so up to torsion. This is contained in the image of this. So you can really find an MA doing the job. And now I can explain very quickly why it's useful, because then you have C to A, LA living as a line bundle over A. The pullback here above C. But if you ask it, so LA prime, so that's this is trivial. Okay, by modifying by an MA, this means it's as a scheme times the same thing as C times A1. And because it's C times A1, you can figure out a section here. Section 1. Okay, and you can follow this section along this road, and so you get something that sends C inside LA prime, and even it doesn't touch the 0 section. So you get something, you can lift C to A from C to LA prime star outside the 0 section, and that's how you can actually take a good p-adic height and get this method, this version of quadratic Chabauty to run. And that's really the important hypothesis. Okay, now I'll explain. So this was very general, but now I'll explain why this can work for this family of modular curves. All right, why we can find something like this. And you'll see it's a bit surprising. Why? What happens? So to sum up, we need to find a quotient where rank equals dimension, and row is at least 1, and then hope that we can sort of, by luck, taking LA like this. So taking LA so that this is actually inside J of Q, hope that it's actually inside A of Q. So in some things smaller. All right, so let's again look at the facts. It was sort of implicit on what I said on quotients, but now I'll split this using this. So it's a well-known fact for modular Jacobians. If I look at length of p square plus nu, it's basically isogenous to products of AFs. Well, I have to be a bit careful here for the AF. So F. So look at F eigenform here inside S2 gamma naught of p square plus nu, and have to only take one inside each orbit by the Galois action. Okay, so each one gives one AF. Otherwise, I would have repetitions and I don't want them. So I take this kind of set. Let's call it B. Here, so I look at all the possible orbits of modular forms in there, define the AFs, and so J naught p square plus nu is the same thing as the product up to isogeny. Okay, in there I'll define something by 2 criterion. So if you recall what I said before, we already know, and this is known by the sign arguments. We know that for every such f, L of f1 is 0. No, I have no choice here. So the next thing is L prime. Okay, let's say AH of P is the product of all f in B, so that L prime of f1, L prime of f1 is non-zero. Here, AFs, and B, it's supplementary. So B will be the ones where L prime is actually equal to 0. All right, and I'll call it a name. I'll explain later. Let's say it's the Heegner quotient. All right. Because of what we know about the forms, and by Kolivegen-Lugachev in this, so L of f1 is 0, L prime is non-zero, so the order is 1. We know the rank of each of those. It's the dimension. So we have the rank of AH of Q is the sum of the ranks, so it's sum of the ranks of AF, it's the dimension of AH. Okay, and actually I can also show the row, so the endomorphisms, there are lots of them, and it's also row AH. Okay, so we are in a good position to hope for a good quotient of rank equal dimensions, but we need this to be larger than 1. Okay. Otherwise, we cannot do anything. If it's just an elliptic curve, we cannot do anything. So we want this to be larger than 1, just because we need rho to be larger than 1. In other words, we need to be sure that we have at least two orbits of functions like this, or the size of this is at least 2. Well, here's where it gets sort of natural. The good news is now we are looking at only vanishing of derivatives of functions. We have analytic tools to do it, even for large primes. And this is what we use now. So let's see here. So to recall, so the first goal is prove that dimension of AH is larger than 1. Okay, and second, so this will imply that we might find an LA such that this lands inside J of Q. Okay, say this is condition star here, and hope once we have this, which is sort of the base condition, hope star still holds. Okay, so this is stronger in general, it's stronger than this, but let's hope it works anyway. Or at least prove, let's say hope, well, not, we just hope, we don't just hope, we prove. So that's what I'll do. Okay, so now this is now a matter of sort of counting how many forms like this have L prime different from 0. For this, we have very good tools, which are trace formulas. And here, I'll just mention Peterson trace formula. So it's meant to compute sort of averages of products of coefficients over orthonormal basis of spaces of modular forms. I'll just give what it says for us here after computations. I take m is equal 1 or 2, and I look at this, which might be a strange looking expression, but that's basically just taking what the trace formula gives you. Okay, we take what it gives us, and you'll see what's really powerful. So F is in basis of S2 of gamma 0 p square plus nu. Okay, and I look at AM bar of F, L prime of F, and I divide by the Peterson norm F square. It's the kind of averages you get with the method, right? Why is it good? Because we can prove that this is growing in P slightly in this shape. This is a constant. This is C minus M, and the error term goes to 0 when P goes to infinity. The first immediate conclusion is that when you take M is equal to 1, okay, and P is large enough, well, the main term is log of P. So the only thing you want to take out from this is that for M is equal to 1 and P large enough, this is non-zero, right? And because I just take any basis here, but it works for, orthonormal here, I could take a basis of eigenforms here. It means that one of them has to be non-zero in the sum. And well, you look at the numerator, it means one of these has to be non-zero at least. Okay? So I'm already sure that this is non-trivial. First good news. But we need slightly more. We need that this is of dimension at least 2. Okay, so it's better maybe to work by contradiction. What happens if this is of dimension only 1? It means there is only one form such that this is non-zero, okay? And the AF is of dimension 1, which is actually meaning that there is one form with coefficients in Q, actually said if you normalize, with L prime non-zero. That's the only way you can contradict this for P large enough. But we also prove, and you see this, we have, if you look at A2 L prime divided by A1 L prime here, when you look at these estimates, you realize that also, yeah, it has to be a real number. This belongs to 0, 1, or P large. Okay, just because of these estimates, you see the M intervenes here. So it's slightly less for A2 than for A1, which means this has to be belong to 0, 1. And when you think if you had only one form non-zero with coefficients in Z, A2 would be an integer. So you get A2 over A1 non-zero and not 1. It's not possible. So because of this, for P larger than at least 290, dimension of AH is at least 2 by these purely analytic means. And then you can fill out the results with all this. Okay, so we have proven that there is a, let's say, a rank equal dimension quotient, which is large enough here. By the way, I should mention, this is, I think that might be the least optimal asymptotic version of trace formulas I know. Many people just do it for something non-zero, which is fine, but then they give estimates of the number of non-zero terms, etc., etc. If I had to give you the estimates in the whole basis, we know that it's at least asymptotically at least 3/4 of such forms which are non-zero. Okay, for L prime, right? But the thing is, the asymptotics are very bad. You know, it's I think we even expect it goes to 1, but asymptotically, the estimates we are given are very bad. So it's very hard to get something effective from this. And we wanted to be able to compute the rest. This is sort of very weak version, but allowing us to, you know, it's quite efficient in convergence. So you only have to compute finitely many cases afterwards, right? So just, it's not expected to be very precise or anything. Okay, so that was the first thing. Second was hope for this. So we know there are LAs so that this belongs to J of Q, non-trivial, but why would it belong to A of Q? And that's where something which I honestly think is a bit of a miracle happens. And there we have to dive into the reasons behind Kolevagin-Logachev. For Kolevagin-Logachev, as I said, it's based on Gross-Zagier work. So Gross-Zagier, I don't have time to explain a bit more, but is inside in Kolevagin-Logachev work. And it uses Hegno points. To give a quick summary, Gross-Zagier tells you when some points which are called Hegno points are torsion or not inside the AF, depending on the value of, I'd say right here in the value of L prime. Okay, what happens here is that the AH is where L prime is non-zero and the Gross-Zagier of the Hegno points are non-torsion. Okay, they're built for this, and so you can even prove they generate the rational points. But the B here is exactly where they become torsion. Okay, supplementary by construction, it's where they have to be torsion. And the thing is, we know that the image, weird image we wanted to figure out is actually torsion. So let's just say this. When I go from the endomorphism from JNS plus SP here, dagger to the group Severi here to it's equal group of X SP Q here. So let's say 0, 0 here. When I go from there to there by the process I described before, the image is generated by Hegno points. Which means that it's not possible to take something from there and land inside B. I all have things in A here, which means what was, I guess, might be a strong condition otherwise. Here it's automatic for non-split Cartan modular curves. Everything working, landing inside J of Q up to torsion, it actually lands inside A of Q for the Hegner quotients, or AH. So this was for free here, some sense for the modular curves we look. Okay, I don't have time to write the conclusion, but I'll just say it briefly. This means, or maybe I can write here, if you can complete yourself. Here, the method, it's quadratic Chabauty. It works in principle for all primes, p larger than 13, on my side, using a rank is equal to, using the Hegner quotient, so very special quotient inside the Jacobian. And here, of course, there is no improvement for practical computation, but hopefully it proves that we can go from all the primes and maybe find one day a method allowing us to do this without having the explicit equations. Right, sorry for going a bit over time. Thanks for your attention.
Thank you, Professor Samuel Lefon, for your wonderful talk. So are there any questions or comments? Quick questions, comments? Yeah, please.
Mm-hmm. Mm-hmm. Ah. Yeah. Yeah, why not? Yeah, I haven't thought about that, but yeah, maybe it would be a bit more direct. Yeah, yeah. Okay. Thanks. Mm. Oh, I think for non-zero degree, the problem is you will have no chance of being trivial, so there, you cannot lift anything here. Not possible. I think that's, yeah, something that's the issue. That's the degree. The degree is like the basic abstraction to do this, and then the second one is this. Yeah.
Yeah, are there any more questions?
By the way, maybe I'll jump on Nathan's remark to say, because I forgot to say it, this works for nx s plus of p. Okay, it also works for x naught plus of p, and the same thing. So quotient of x naught of p by the frequent involution, which was also not doable before. Same computation that be done, it also works.
Any more questions, comments? Yeah, otherwise, please thank the speaker. Thank you.